Now, last day we talked about we saw the basics of the single server queuing system, and we saw certain definitions pertaining to those systems. Now, today we will move on to derive the relevant equations and relevant say performance measures for a single server queuing system. So, our queuing system is MM1 and infinity. Now the assumptions in this case are the arrival process are Poisson's arrival, the arrival population is unlimited, and the service time is represented with an exponential distribution. All arrivals wait to be served, and lambda and mu are constant. And the most important thing, this service rate, average service rate should be greater than or equal to the average arrival rate. We'll see later on why this condition is needed. Now to really derive the equations, we will start with a birth-death process. So we'll assume that arrival of a customer is a birth to the system and departure of a served customer is a death in that particular system. So in a steady, here we have represented with a state diagram. So here this state 0 represents that there are no customers in the system. So there is a 0 customer in the system. There is one customer in the system, and so 0 customers in the system, 1 customer in the system, 2 customer in the system, and so on. So in a steady state, the rate in should be equal to the rate out, or the mean entrance rate should be equals to the mean departure rate. And the sum of also, we will find out what is the probability of having a 0 customer at any particular instant. Similarly, this represents that what is the probability of having just one customer in that total system. What is the probability of having 2 customers in that particular system? And sum of all these probabilities in a steady state should be equal to 1. It should not be 0, it should be 1. I'm sorry, this probability should be 1. So at state 0, now at state 0, so how we can reach to state 0? So we can reach to state 0, how we can reach to, how we can move on from state 1 to state 0. So basically from state 0, so if we have, and all these lambda here are equal, so in a general case we can have lambda 0, lambda 1, lambda 2 different and mu1, mu2 different, but in our case we are assuming that mu1 equals to mu2 equals to mu I, and similarly here we have lambda 1 equals to lambda 2, and so on and so on. So in a steady state, lambda p0, so the probability in having state 0, and with a lambda arrival it will come to state 1, and then in state 1 with service rate mu, so from state 0 it can move to state 1 with a chance of, so probability of p0 into lambda, and from state, so rate out from 0 to 1 is p, so probability of having state 0 multiplied by lambda is the probability of going from this state to this state. Similarly, this is probability, this state p1 is represented by this one. So p1 into this mu will give us the probability of moving or going from, or so rate in to state 0. So rate out from state 0 is lambda into p0, and rate into the state 0 is mu into p1. And according to the steady state principle, birth-death modeling, the rate in should be equal to the rate out, or the mean entrance rate should be equal to mean departure rate. So that gives us this equation. So lambda p0 equals to lambda p1, mu p1. And from here we can find out p1 equals to lambda by mu into P0. And we can represent this lambda by mu by a variable called as rho. And state 1, similarly, if we analyze state 1, so from state 1, it can go out to state 0 as well as state 2. So total rate out is total rate out is mu p1 plus lambda p2. Plus lambda p1. Mu p1 plus lambda mu p1 plus lambda p1. So this is out rate. This is out rate. And in rate is, if you see here, coming the in to P1, state P1 is from 0 and 2. So from 0 it will come with lambda P0, and from 2 it can come through mu P2. So lambda P0 plus mu P2 is this. And now we can find out mu P2 by rearranging this equation. Mu P2 equals to mu P1 plus lambda P1 minus lambda P0. Now P0 can be represented as lambda P0 can be represented as mu P1 from this equation. Lambda P0 is equals to mu P1. So mu P1 we can cancel out. So mu P2 equals to lambda P1, or P2 equals to lambda by mu P1. So we can say rho P1, or if we represent this P1 with rho P0, then we can write P2 equals to rho square P0. And so on. So if we move on, in a general case, we can write Pn equals to rho to the power n P0. In general, we can say this. And now the next equation says that summation over all pi's, as we have told at the start, that the sum of all the states should be 1. So sum of p0 plus p1 plus p2 plus p3 and so on up to infinity. So starting from I equals to 0 to infinity, pi equals to 1. So now we can represent this pi with the help of lambda by I to the power, lambda by mu to the power I p0 equals to 1, or rho to the power I p0 equals to 1. And from here we can find out sum of all this quantity. So if this rho is less than or equals to 1, then sum of I equals to 0 to infinity rho to the power I will give us 1 by rho. So now we can write p0 1 by 1 minus rho equals to 1, or p0 equals to 1 minus rho. So p0 equals to 1 minus rho. So this is our first equation. So this is a probability. This represents a probability that there is no customer in the system, or the system is free, or the server is free. Now from here on, we will move on to find out the expected length of a queue in a system, or expected persons in the system, total system. To find out that, we will use this sort of technology, expected value. So for example, if we roll a dice, a fair dice consisting of number 1 to 6, then what is the expected value we can expect? So the expected value will be, what is the probability of coming 1? So the probability of giving 1 from or getting 1 from that dice is 1 into 1 by 6. Similarly, 2 from that dice is 2 into 1 by 6. 3 from that dice is 1 by 3 into 1 by 6, and so on. So if we sum them all, we will get 3.5. So 3.5 is the expected value from the dice. Although if we roll a dice directly, we will not get 3.5. We will never get 3.5. But if we roll that dice say 100 times, then the total sum which will appear will be 3.5 into 100. So it will be around, say how much? 3.5 into 100. So 35. So this is what we will get. So we'll apply this similar analogy to find out the expected length of persons in that particular system. So expected length of customers in the system will be ls equals to I equals to 0 to infinity I into pi. And now this pi can be broken down into rho to the power I p0. Now we can write this rho to the power I p0. So we can take one rho and p0 outside. So we have taken one rho and p0 outside, and now we can write I into p to the power I minus 1. Now we'll get this number if we differentiate p to the power I. So d of d rho to the power I will give us this number. So now let us write that. So in a reverse way. So we could have got this number by having this differentiation. So d by d rho of rho to the power I. And now we can add this, we can take this differentiation outside and summation inside. So if we take this summation inside, so what we will find out, so p0 into rho into d by d rho summation over rho to the power. So this is rho, not p, this is rho basically. Rho to the power I. And rho to the power I, summation over 0 to infinity, rho to the power I is 1 minus 1 by rho. So if we differentiate that, we will get p0 into rho by 1 minus rho 0. Now this p0 can be written by or substituted by 1 minus rho. So 1 minus rho into rho by 1 minus rho square. If we simplify this, we'll get rho by 1 minus rho. So this is the expected length of or expected number of customers in that particular system. If we can further simplify it in terms of lambda and mu only, we'll get this. And if we just try to find out how many customers are there in the queue, then the number of customers in the total system is equals to number of customers in the queue plus expected number of customers which are being served. And expected number of customers who are being served is lambda by mu. So we can write ls equals to, this is lq, I'm sorry. So lq equals to ls minus lambda by mu, or lambda by mu minus lambda by mu. So we'll get lambda square by mu minus lambda. So this is the first or the second equation we'll derive. Then we have a Little's law. So to derive the other equations, like the average waiting time. So here Ws represents the average waiting time in the system and Wq represents the average waiting time in the queue. So this can be derived by using Little's law. So in a Little's law says that whenever there is a arrival and departures and there is a black box, the servicing which is going on, then the average number of customers in the system is equals to the arrival rate multiplied by average time spent by the customer in the system. So average system time. So average rate, arrival rate multiplied by average time spent by the customers. So now we have the formula for average number of customers in the system. Arrival rate is known by lambda and average time is unknown. So Ws is unknown. So from this equation we can find out Ws equals to Ls by lambda or lambda by mu minus lambda into lambda. So 1 by mu minus lambda. Similarly, in terms of LQ, if we want to find out, so this will be lambda into WQ, or WQ equals to lambda by mu minus lambda. So if we just write it in a single sentence, so we can say rho, which is also known as server utilization. So server utilization is lambda by mu. Average number of customers waiting equals to, this is in the queue. So lambda square by mu into mu minus lambda. Average number of the customers in the system is rho by 1 minus rho, or lambda by mu minus lambda. Average waiting time is in the queue. Average waiting time in queue. This queue represents queue. So lambda by mu minus lambda, or in general, I have just given a snapshot here. So rho is equals to mu minus lambda by mu. Pn equals to 1 minus rho to the power n. L equals to lambda by mu minus lambda, or rho by 1 minus rho. W equals to 1 by mu minus lambda, or 1 by mu 1 minus rho, length of queue only is this, and waiting time in the queue is this. So with this, let us move on to, I hope this, so let us move on to an example, and then probably we can see. So now if we assume that average arrival, there is a Ireland muffler shop and the customers arrived at an average of 2 per hour, and whereas the service time is 20 minutes. So arrival is lambda is equals to 2 per hour, and if we compute the service time in terms of hour, then the service per hour is 3. So we can now say that lambda is 2 and mu is 3. So from here we can find out the utilization, average server utilization is 2 by 3. Probability that there is no customer in the system or the server is free is 1 by 3. Probability that there is just one customer in the system is 2 by 3, and which is being 2 by 9. Probability that there are 2 customers in the system is this one. Probability that there are greater than 4 customers in the system is this one. Similarly, the average length in the system is 2 customers. Average waiting time of a customer is L by lambda, which is 1 hour. This is average waiting. This waiting time also includes the time which is being used for servicing. If we just want to find out what is the average time which is spent in the queue, then this is W minus 1 by mu, and this is 2 by 3 hour. Average number of customers in the queue only is 4 by 3. This one is the total number of customers including those who are being served. Here, this is the customer who are waiting in the queue only. Again, the number of customers who are in the queue plus expected number of customers who are expected to be being served is lambda by mu, because this is server utilization. So if we add, we'll get the same quantity what we have got earlier also. So this is I will also give one more example, more concrete example. So I will just you can read it out, you can see it. So customers arrive at one person barber shop according to a Poisson process with a mean inter-arrival time of 20 minutes. Customers spend on an average of 15 minutes in a barber's chair. Now we need to find out what is the probability that a new arrival need not wait for the barber to be free. What is the expected number of customers in the shop? How much time can a customer expect to wait for his turn? That means the customer has to spend in a queue. How much time can a customer expect to spend in the shop? That means this is the total time which is there in the queue plus the haircut time. Then the management is thinking of another chair and hire another barber if the customer's average time in the shop exceeds 1.25 hours. How much the average rate of arrival increase to warrant a second barber? Now with this, let us try to solve it. So arrival rate here is, so here if we see it's 20 minutes. So mean inter-arrival time of 20 minutes and service time is 15 minutes. So if we move it into if we convert it into hour, so arrival rate is 60 by 20, so 3 per hour, and service rate is 4 per hour. Now P0. So the first question is, what is the probability that a new arrival need not wait for the barber to be free? That means the server is already free, so whenever the customer comes, he can directly sit into the barber's chair and have a haircut. So probability that there are no customers in the system. So that is 1 minus lambda by mu, and that's 0.25. So there is a probability of 0.25 that the customer doesn't need to wait in the shop. The total length or total number of customers in the system or in the shop is lambda by ls, lambda by mu minus lambda, so which is 3 in this case. Average waiting time of the customer in the queue is lambda by mu into mu minus lambda. So if we solve it, it is around 45 minutes a customer has to wait in the queue. And the total waiting time in the whole process, including the haircut, So that will be 60 minutes. And now the last question. So last question is, the management will increase or add another chair and another barber if the customer's average time in the shop exceeds 1.25 per hour. So let's say that the waiting time is 1.25 hour. So that means lambda by mu into mu minus lambda is 1.25. So if we solve it, so lambda is 20 by 6 hours. That means around 18 minutes is the inter-arrival time. So earlier inter-arrival time is 20 minutes. So if the inter-arrival time is decreased to 18 minutes, then the management may think of adding a new chair. So that's what the first problem says. We'll go with another problem also, slightly different. I hope you are getting this. The machine in production, so another problem, the machine in production shop breakdowns at an average of 2 per hour. The non-productive time of any machine costs is 30 per hour, rupees 30 per hour. If the cost of repair person is rupee 50 per hour and the repair rate is 3 per hour, calculate the number of machines not working at any point, average time that the machine is waiting for a repair man, and cost of non-productive time of machine operation, and expected cost of system per hour. So now here arrival rate is 2. So breakdown is here, the service the machine is that forms a queue. So average arrival rate is 2 and the service rate is 3. The repair rate is 3 per hour. So the number of machines not working at any point of time is equals to the number of machines waiting for repair man plus machines being repaired. So both, that means those who are in the waiting queue. So those who are in the waiting queue, those machines are basically not used for any productive productive things. So we can say that these machines are not working at this particular time. So LS we need to find out. So LS equals to 2 in this case. Another one was, what is the average time that this machine is waiting for a repair person? So this is the waiting time in the queue, and the waiting time of the queue is 40 minutes here in this case. The third question is cost of non-productive time of the machine operator. So the cost of non-productive time of the machine per hour is average number of machine not working into rate. So average number of machines not working is already 2. We have calculated it 2, and rate of, so this the non-productive time of any machine is rupees 30 per hour. So if we multiply those two quantity, we'll get the cost of non-productive time of the machine per hour. And similarly, the expected cost of system per hour. So this is the cost of waiting plus the cost of servicing. So cost of waiting is 60 and the cost of servicing is 50 per hour. So the total expected cost of system per hour is rupees 110. So for today, we will stop here. I hope that you have got the basic idea of how a single server queue where arrival rate and service rate are memoryless, that means Poissons and exponential, can be modeled, and how the formula can be used to compute for working examples. So thank you.